So Lewis acid base, these are just electrophiles and nucleophiles, okay? Really quick, every reaction, seriously, every reaction we'll ever see is either an acid-base reaction, in which case I'm talking about a Bronsted-Lowry acid-base, or a nucleophile-electrophile reaction, okay? Which is also Lewis acid-Lewis base, okay? But again, the acid-base kind of melds it all together. So just see it distinctly as an acid-base reaction or an electrophile-nucleophile reaction. And what's the difference between these, right? The acid-base transfers a proton, and the electrophile-nucleophile is everything else, okay? So pretty much if you are attacking an H, you're an acid-base. If you're attacking anything else, it's an electrophile-nucleophile. It's really either or. It's not both, okay? So in these Lewis acid-base problems, or the nucleophile-electrophile, right, the nucleophile attacks with electrons, okay? So it donates, that's why it's a Lewis base, but again, the nucleophile attacks, whereas the electrophile gets attacked, okay? So nucleophile attacks, electrophile gets attacked, and so we start arrows at electrons and end at atoms. So if I were to give you this guy plus BH3, let's say I just gave you the product, here we go. How did this form? Just think about the electrons. Think about the electrons. There's no two electrons between the oxygen and the boron, but now there is. Okay? Again, there's a formal bond here. There was not before. So we had to take two electrons from somewhere and form a bond. So where did those electrons come from? Okay? The bottom line is we don't know much about boron, but we do know a lot about oxygen, and we've seen oxygen do a lot of attacking. And so that's what's going to happen. The oxygen is going to attack the boron, and again, in doing so, we take these two electrons that were on the oxygen, and now we're going to share them between the oxygen and the boron. So that makes a bond. Okay? So here, which one's the nucleophile? Which one's the electrophile? Nucleophile attacks. Here's the nucleophile. Here's the electrophile. Electrophile gets attacked. Okay? And yes, if you want to be distinct, this is the Lewis base, this is the Lewis acid, this is the Lewis acid base, Lewis acid, Lewis base complex, but I don't care as much. Something more like what we'll see, something like this, where I gave you guys the products. I gave you something like this in multiple times. Okay, so now we've got a plus charge there and O minus there. Okay, so let's think about this. Again, there's no bond between the nitrogen and the carbon here, but now there is. So somehow two electrons that were not between the nitrogen and the carbon are now between the nitrogen and the carbon. Does the carbon have electrons? It could form a bond with nitrogen. No. It's got this double bond, but do you see that the nitrogen has a formal lone pair? I think that's a lot more mobile than the double bond. And by the way, if we took the double bond, then we would be leaving a plus charge. It doesn't quite work. Okay? Plus, also, if we attack the nitrogen with our double bond, nitrogen's already got 10 electrons. Sorry, already has 8 electrons. So we can't take the double bond and attack the nitrogen. Okay, so instead it makes more sense for the nitrogen then to attack the carbon. Because the thing is, we would expand its octet by forming this bond, unless we do something with 2 of its electrons. We've done this multiple times now. Just kick them up to the oxygen. And that's how the oxygen then ends up with a formal -1 charge. Okay? Again, think about the movement of electrons. There was not 2 electrons between the carbon and nitrogen, and now there are. So where did those 2 electrons come from? It doesn't make much sense for them to come from the double bond, or the C double bond O, because then we would be attacking the nitrogen. The nitrogen already has 8 electrons. So instead, let's use the nitrogen's lone pair, attack the carbon, because we can then kick 2 electrons up from its double bond onto the oxygen. Sweet. One more, really quick. What's the nucleophile here? Does the attacking. Here's the nucleophile. Electrophile gets attacked. Sweet. And one more. I plus NaSH goes to SH plus NaI. Always remember that whenever we have a sodium or a potassium or any metal involved, this is an ionic bond. So it actually looks like that. Go ahead and rewrite it just like that. If you ever see a metal right next to an atom, just go ahead and rewrite it. So then, what am I going to do? Again, in the product we have a formal SC bond that's not present here, okay? And so we have to put electrons between the S and the carbon. How do we do this? Does the carbon have electrons we can attack with? No. Does the sulfur? Yes, because it's just like oxygen. So it's actually got 3 sets of lone pairs in there. Because the sulfur is just like oxygen. So let's take one set. Let's attack the carbon. Again, we can't expand carbon's octet. Something has to happen. What if those electrons left with the iodide? Now we would have a bond between the sulfur and the carbon, because that's exactly what this arrow is showing. And then the iodine has a minus charge because the sodium's got a plus charge. Sweet. What's my nucleophile? Does the attacking. Here it is. What's the electrophile? Gets attacked. There it is. Alright, so that's it for Lewis acid base, MO theory, and hybridization. Here I have lots of notes. Okay, MO theory deals with molecules, orbitals, okay, whereas hybridization deals with the atoms, orbitals. We use MO theory to explain reactivity, whereas with hybridization we use it to explain shape. Okay, so in MO theory we talk about HOMO and LUMO. Remember, the nucleophile uses its HOMO electrons to attack the electrophile, or the lowest unoccupied MO of the electrophile, and that's what gets attacked. So we are actually filling the LUMO with the HOMO electron. Remember, it does the attacking. We use the electrons to attack. We are attacking the LUMO. Okay, so here you do need to know the shapes of a sigma bond, a sigma star bond, antibonding orbital. You need to know the shapes of a sigma orbital, molecular orbital specifically, a sigma star molecular orbital, pi, and a pi star molecular orbitals. Okay, remember we went through those shapes, and when we are filling and attacking the antibonding orbitals, that's how, those are the electrophiles. The electrophiles have the LUMO, and so when we fill or attack them, then we break a bond, and that's exactly what's going on. I went through that whole water reacting with HCl example. I'll go back and look at that. And so in terms of hybridization, it's a different argument in terms of bonding, because here we're talking about the overlap of hybridized and unhybridized orbitals. Okay, so remember that single bonds are always sigma bonds, which are formed by the overlap of hybridized orbitals, and that double bonds consist of a sigma and a p, right? Sigma and a pi. Okay, and triple bonds are made from a sigma and 2 pi bonds. Okay, and the pi bonds are made from the overlap of the unhybridized p. Okay, so really quick, I think I'm going to focus mostly on the hybridized stuff. Okay, because here, as long as you understand exactly that where HOMO attacks the LUMO, and then understand the shapes of those molecular orbitals, you're good. So how about NH2? NH2 minus. Okay, so this guy looks like this. What is his hybridization? The nitrogen. He's got 4 groups. Each lone pair counts as a group. So 1, 2, 3, 4. He is sp3 hybridized. Okay, and so this bond here, how is it made? Okay, it's made from the overlap of hybridized orbitals. Well, in this case, it's going to be the hydrogen's s orbital plus the nitrogen's sp3 orbital form the sigma. So if we could kind of draw that, here's one of nitrogen's sp3 orbitals, and here's hydrogen's s orbital. Okay, I didn't make that very large. I should have made it a bit bigger. Here. Okay, so here is our sp3, here's our s, and they're overlapping. And so that's how this bond is formed, and then the other lone pairs are inside of the nitrogen's sp3 orbitals. How about COH? Really quick. This guy. Really quick, the hybridization of this guy. He is sp2. Hybridization of this guy. He's also sp2, because although they aren't drawn, he has lone pairs. Okay, don't forget those lone pairs. Okay, so importantly, this bond, let's talk about this bond, what is it made from? Okay, this is a single bond, so it's a sigma bond, and it's made from, again, the hydrogen's s orbital overlapping with the carbon's sp2 orbital. Okay, so carbon has 3 sp2 orbitals, right? 3 sp2s and 1 unhybridized p. How did I know that? Because it's sp2 hybridized. If you're sp2 hybridized, you have 3 sp2 orbitals and 1 unhybridized p. Always totals 4 orbitals. Okay, go back and review those in your notes. So here are his sp3 hybridized orbitals. sp2, sorry, sp2, sp2. Okay, and it's trigonal planar shape. Okay, and the oxygen also has its sp2. Okay, so imagine it also has sp2 hybridized orbitals. And so importantly now, that double bond, what is it made from? It's actually made from a sigma bond from the carbon's sp2 and the oxygen's sp2. Okay, so imagine the same sp2 orbital coming from the oxygen. They overlap right in the middle. I know these drawings get really complicated, but there's oxygen's sp2. You can see they overlap right in the middle. Okay, but it's a double bond. Double bond's made from a sigma and a pi. So it's also got a pi made from what? The answer is the unhybridized p's from the carbon and the oxygen. Both of them have an unhybridized p. So let's just draw it right there and right there. Unhybridized p right across the double bond. Sure. There we go. Okay, so again, if you are sp2 hybridized, you have 3 sp2 orbitals and 1 unhybridized p. If you are sp hybridized, you have 2 sp hybridized orbitals and 2 unhybridized p's. If you are sp3 hybridized, you have 3 sp3 hybridized orbitals. It's always how it goes. Okay, I don't have time to really go over any more. Send questions my way.